Yes, hi again, everyone. Now we're going through midterm 2016 questions. Now, starting with question one, you are traveling on an elevator moving up. What is the force that is opposite but equal in magnitude to your weight? So we're looking again at an elevator moving up, and you are inside the elevator like this. Now, we're asking you for the force, okay, that is equal that is opposite but equal in magnitude to your weight. So if your weight is like this, okay, pointing down, that's Earth pulling you downward, okay. But then we want the force that is opposite but equal in magnitude to your weight. Now, of course, if we're looking at the normal, from the surface, okay, so the reaction from the surface of the elevator. Now, this normal will depend on whether the elevator is accelerating upward, accelerating downward, now, or it's moving with constant velocity. Now, so you may be feeling heavier, you may be feeling lighter, depending on whether you're accelerating up or down. But we won't, so that means what? That means sometimes the normal can be greater, okay, which means not equal. And we want the force that is opposite and equal in magnitude or weight, regardless of whether the elevator is accelerating upward or downward. So the only one actually here that will be always equal but opposite is the force of U on Earth, okay? That will be the same regardless of what you're doing, whether you're moving up, down, accelerating up or accelerating down. So the force of U will be the force you are pulling Earth towards you. So this is going to be force U on Earth. So Earth is pulling you downward with the weight W pointing down. And this other force, you can call it negative W. So this will correspond to the force of U pulling Earth towards you. Okay, so this is then the answer to this question. Now, question number two. Now, we had a very similar question in midterm 2017. The numbers are slightly different, but the idea is the same. So we're looking for the net force along x is equal to mass times acceleration, and we want you to find, the magnitude of kinetic friction acting on the crate. So given that this is the force you're applying, the mass of the crate and the acceleration, now the same steps, exactly the same steps we did in midterm 2017, and you end up with friction equals to magnitude of force minus mass times acceleration, okay? And the idea is very similar. You end up with this value for the friction. Again, no need to repeat the same steps from that midterm. Question number three, we have a truck moves forward with a constant speed and has a crate in its cargo bed. If the truck suddenly slows down and the crate does not move against the cargo bed, in what direction is the frictional force that the floor of the cargo bed exerts on the crate? Again, similar question, okay? So this is the truck. The crate, again, initially the truck is moving with constant speed. Okay, so let's say this is velocity v. And if the truck suddenly slows down, which means acceleration is pointing to the left or backward. Now, when acceleration is to the left, that means the crate wants to move forward. Okay, so this is again inertia. Now, if the truck suddenly, the truck suddenly slows down and the crate does not move, okay, against the crate, in what direction is the friction force? Now, of course, to prevent the forward movement of the crate, I need a force to oppose that. So I need a force that will go against, which will be the direction of friction, which is, 1 second, backward here, yes. So the correct answer then is the friction is pointing backward. Great, so this is question 3. Question number 4. We also had something similar to this. Now here, we're looking for two weights, one with mass 3 kilogram, that's mass M1, and the other is 13 kilogram, mass 2, attached at the end of a massless string that hangs over an ideal pulley. Now the system is allowed to move freely. What is the acceleration of the system? Okay, what is the acceleration of the system? Now, of course, we apply Newton's second law on here, let's say for mass number 1. Okay, so that will be, if I put, I take positive y pointing upward, so tension will be positive, the weight will be negative, and acceleration, okay, for let's say mass 1, now I notice mass 1 is less than mass 2, it will be accelerating upward. So acceleration for mass 1 will be taken as positive. Okay, so I'll write tension, positive, minus mg, again, weight is pointing downward, is equal to m1 times acceleration. Okay, now here, if you take mass 2 now you can consider the direction of y as being pointing upward, or you can follow the direction of the acceleration, the direction of motion, because it's driven by the downward motion of mass 2. Now, in which case, if we choose the positive y to be pointing downward for mass number 2, it's the same thing. We'll end up with exactly the same thing. Okay, so if I choose positive y pointing downward for mass number 2, so the weight now will be positive, tension will be negative. Okay, again, you don't have to. You can stick to having a positive y pointing upward, with still tension being positive, like we had a negative M2G, but then you would have, on the other side, you would have negative M2A if we did that, okay? So the acceleration would be negative if we took positive y pointing up. Now, here I have equation 1, equation 2, okay? And what I'm looking for is the acceleration. So keep in mind, my unknown here is the acceleration. So here, if I add equation 1 and equation 2, that was the reason why we chose the second equation to follow positive y pointing downward, so that we can cancel the tension. So you see here, in equation 1, tension is positive, in equation 2, tension is negative. When you add the two equations, you cancel the tension, okay? So you end up with mass 2 times gravity minus mass 1 times gravity is equal to m1 times acceleration plus m2 times acceleration. You solve for acceleration, of course, you factor for acceleration, and then you divide by the total mass m1 plus m2, and this will be your acceleration, okay? And the value is about 6.1 meters per second squared. Now, question number 5. A block A rests on a frictionless level surface and is attached by a light string to a 10 kilogram block B. Okay, so hanging mass where the string passes over a massless frictionless pulley. Now, if the tension in the connecting string is 56 newtons, find the magnitude of the acceleration of the blocks. Now, same idea, we're looking for acceleration. Now, Newton's second law for block A, okay, moving horizontally, so the only force acting is the tension. Okay, so this is a tension acting on block A. So the net force will include here for block A only tension, and it's equal to mass of block A times acceleration. Now for block B, same idea. So if we consider positive y following the direction of the acceleration, again, you don't have to. It's just to make it easier to make the acceleration turn positive, because the acceleration is pointing downward. So it's more convenient, easier to have the acceleration following the direction of your axis. Now here, in this case, mg will be negative. Sorry, mg will be positive because, again, positive y is pointing down, but tension will be negative, equal to mb times acceleration. Now I take acceleration as positive because it's following the y-axis. Right. Okay, so we have these two. So same idea here. Okay, so you can add the two equations. Okay, so cancel the tension. The tension is the same for both. Okay, so you end up with the following. So we have, 1 second. Right, sorry, so instead of adding the two, because in this case, we actually know the tension. Okay, so we can use it straight away. Confusing with the previous one. So in this case, we actually know the tension. We can just use equation B to answer this question. So in equation 2, okay, we know actually everything. So we know the mass, we know the tension, we know, of course, mass is given. So we solve for acceleration. Okay, so when we plug the numbers, so we have 10 times 9.8, so 10 kilograms on 9.8, minus 56 for the tension equals to the mass 10 times my acceleration, which is the unknown. So we solve for acceleration, and this will give us straight away the acceleration equal to 4.2 meters per second squared. Okay, so it's a lot easier. Okay, so you don't even need to combine the two equations. Tension is provided in this case. Now, question number 6. The figure shows two bodies of masses capital M and lowercase m. Now, the big block capital M is placed on a horizontal surface, and the lowercase m, smaller mass, is placed or is hanging at the side, connected by a light cord over the massless and frictionless pulley. The masses are 9 kilograms and 4 kilograms. What is the minimum coefficient of static friction between the horizontal surface and the big block M, so that the system is not moving? Okay, so we're looking for the minimum coefficient of static friction. Okay, so that the big block capital M is not moving. Now, in this case, I'm looking for what? I'm looking for the net force equals to 0. So tension. Okay, so tension that builds in the cord. If you focus on block M. So on block M, what is acting is tension, which is to the right. And then you have, so this is the free body diagram. So tension is to the right, and then you have to the left, you have friction, static friction. And we're talking about the maximum static friction, which will give us the coefficient of static friction. So tension, if I consider positive direction to the right, minus static friction, maximum static friction. Now it's not accelerating, the block is not accelerating, so let's say it's equal to 0. Okay? Which means what? Which means tension, okay? Tension minus mu k, remember maximum static friction, okay, is equal to a coefficient of yeah, coefficient of static friction. So this is an S here. So minus mu S, okay, times normal, right? So here, the normal is going to be mg, okay, normal is mg, so tension minus mu S mg is equal to 0, okay? And now in this case, for the tension, we still don't know it yet, okay? How can we get tension? If we look at the hanging mass, lowercase m, now if you apply, or if you represent this hanging mass with free body diagram, so you have mg pointing down, it's gravity, and then you have tension pointing up. So this will be tension. Okay. Now I can say, okay, mg. So again, if you choose positive y pointing down, you don't have to. You could use any direction. You can stick to pointing up. So the only difference is that tension will be positive and mg will be negative. So it's equal to 0. That's the most important part. Okay, so the net force is equal to 0, which will give me what in this case? It will give me tension. Okay, so there's two different ways. You can either combine the two equations, equation 1 and equation 2, or you can substitute. Whichever way is going to be the same. Now, when you combine the two, when you add equation 1 plus equation 2, you're canceling the tension, okay? So you end up with mg, the hanging mass mg, minus coefficient of static friction. I think it's still static, okay? Times m times capital mg equal to 0. That means the coefficient of static friction will be lowercase over capital case, and it's equal to 0.44. Okay, so this is then our coefficient of static friction, right? So this is then the answer to this question, 0.44. Now, question number 7. A student in an elevator is checking Newton's laws using a scale. The scale is showing a reading larger than the student's actual weight. Which statement explains this phenomenon? Now, among these options, the correct one is highlighted as the elevator moves downward with decreasing speed. Now, if the elevator is like this, okay, it's moving downward, velocity is pointing down, but because the speed is decreasing, moving downward, that means I must have an acceleration that is opposing this direction of velocity. That means my acceleration is pointing up. Okay, my acceleration is pointing up. Now, we know that if the acceleration is pointing up, remember then the formula for the apparent weight is mg, okay, or between parentheses, mg plus a. So if acceleration is positive, the weight, okay, the apparent weight will be more than the normal weight, okay. Now, among the options provided, okay, I don't have an option which shows me that the elevator is moving upward with an increasing speed. This will give me straight away, this would have been straight away, an acceleration pointing up like this. So instead, I am provided with this option, elevator moving downward with decreasing speed, okay? But that still gives me an acceleration that is pointing up, and that's still, okay, going to give me an apparent weight that is more, okay, than the normal weight, okay? And you can check the other ones are not the correct answers, okay? Because first one is moved downward with increasing speed. That means acceleration is pointing downward, okay? So that will be feeling lighter, okay? Option C, elevator moves upward with decreasing speed, okay? So here, the acceleration will also be pointing downward, okay? And then option D, elevator moves downward with constant speed. So if speed is constant, you won't feel any difference, zero acceleration. So the weight will be the same as the normal weight. And the last option is the elevator moves upward with constant speed, same idea. So if the speed is constant, no change in weight. Now, question number 8, the thigh has a mass of 6.8 units, okay? Now, we're not specifying what units is being used. That doesn't matter as long as I can use it as a measure of mass. And then its center of mass is 9.6 units from the hip joint. Again, we're using this units. So it could be anything, okay? But for now, let's not worry too much about the unit for the mass or for the distance, okay? Then you have the corresponding mass for the, and the length, sorry, for the knee is 2.8 and 33.9, and for the ankle, 1.0, 50.3. Now, where is the center of mass, okay, of the outstretched leg located relative to the hip bone? Now, we're taking the hip bone, this one, as the 0, okay? And we're looking at the center of mass of the leg, considering we have the mass and distance for the thigh. We have the same thing for the knee, and we have it, so the knee is this guy. So the knee is here, and the ankle is here. Okay, the ankle is here. This is the, right. So for the leg, sorry. Now here, sorry, we have, yeah, we have the thigh, first one, of the knee, the second is the knee, and the third is the ankle, right? Now we're using the formula for center of mass. X center of mass is sum mi(xi) divided by sum of all masses, okay? Now, in which case, all I need is plug those numbers provided, okay? So here I have, if it's relative to the hip bone, so mass thigh multiplied by x thigh. Now x thigh is at 9.6 units from the hip bone, okay, and so is the knee, okay, and so is the ankle. These are the measures we have. So we plug the numbers, of course, over the total mass. Again, we're using units, it doesn't matter. You end up with this value for the center of mass, okay, along x. Now, question 9. We had a very similar question in midterm 2017. Now, we're looking at the squid, okay, and the speed at which the water, the bolus of water, the mass of water must be ejected, okay, so that the speed or the squid can escape at a speed of 0.7 meters per second. Okay, so this is before the squid escapes. Okay, nothing is moving. And here, when we talk about collisions or problems like these, you know, throwing something or ejecting something, we look at the conservation of linear momentum before, okay, before the event happens, either throwing or ejecting, etc., and after it happens. Okay, So the total linear momentum before it happens is 0. That this is the sum of total linear momentum before ejecting the water bolus. And then after, I want the squid to escape at this velocity, at 0.7 meters per second. Now, for the squid to escape then, at what speed, okay, how fast must the water be ejected for the squid to escape at that speed? Let's have a look. So net or total linear momentum initial is equal to total linear momentum final. Now initial is 0. We know it because again nothing is moving initially. Okay, so initially nothing is moving, and then when the squid ejects the bolus of water, so we have mass squid, velocity squid, plus mass water, velocity water. Okay. Now, in this case, I know I'm looking for the velocity water. I'm using a plus here. Okay. I will end up with a value that should be negative. Okay, because it will tell me that the velocity is in the opposite direction. Okay, it's going to be pointing to the left if my squid is moving right. So here 0. I'll plug all the numbers. Okay, so mass squid, velocity squid, and then plus mass water, velocity water. Okay, so plug all the numbers. Okay, plug all the numbers. So we have the unknown in this case is velocity. Again, so we're looking at velocity of water. I don't know why did I put squid here. Anyways, so here you solve for velocity water, and you end up with this negative velocity. Okay. Right. Next question. We have a railway boxcar with mass m1 moves with velocity v towards the boxcar of mass m2 at rest on a rail with negligible friction. On collision, the trucks couple to each other. And then if mass 1 is 1.6 m2, what will be the velocity of the coupled trucks after the collision, expressed in terms of the velocity v of mass 1 before the collision? So I'm given this problem, okay, which is an inelastic collision. So mass 1 is moving with initial velocity, v1 initial. Mass 2 is stationary, not moving, velocity 0. Okay, so this is before. After collision, they move together as total mass. Okay, now I want you to express what is the velocity, the final velocity. Okay, what will be the velocity of the coupled trucks after the collision, expressed in terms of v of mass 1 before the collision. Right, so this is the coupled, and it's moving with the final velocity v. Now, same idea, inelastic collision, total linear momentum is conserved before and after collision. Now, before collision, only mass 1 is moving, mass 2 is not, so the linear momentum will come from mass 1. On the other side, you have the total mass times final velocity. Okay? Now, this is typical of inelastic collision. So final velocity will be m1 over m1 plus m2 times initial velocity v. Now, we don't need actually the value of the initial velocity for mass 1. All we need is to express it in terms of this velocity. Okay? Now, we know that m1 is equal to 1.6 m2. So that means I can further simplify. You see here in the denominator, wherever you see m1, you put 1.6 m2. Okay, so wherever you see m1, put 1.6 m2, and then you cancel all the m2s. So you end up with 1.6 over 2.6 times velocity, which is 0.62 times the initial velocity of mass 1. Okay. Great. So question number 11. A 100-kilogram car moving at 20 kilometers per hour collides head-on with a 10,000-kilogram truck moving at 2 kilometers per hour in the opposite direction. Which of the following is a possible motion for the vehicles after collision? Now, the car stops moving, okay, for the first one, and the truck moves in the opposite direction. Option B, both car and truck move in the original direction of the car. Now, the correct answer is the vehicles couple together, completely inelastic, and the coupled vehicles come to a complete stop. So here, first, we need to check, okay? We're given the velocities, okay, and the masses for the car and the truck. So all we need to do is calculate the total linear momentum. Okay, so velocity for the car, okay. And also the mass for the, the mass for the car is 1,000, and then velocity for the car is 20 kilometers per hour. And then the truck is 10 times heavier, okay, multiplied by velocity of this truck, -2, because it's moving in the opposite direction. Okay, so we clearly say that it's moving in the opposite direction. Okay, so the net is then equal to 0, right? So here, if the net is equal to 0, that means, okay, the vehicles, if it's perfectly inelastic, right, they will lock together and then complete and couple and come to a complete stop. Okay, so that's what will happen in this case. Now, question 12, similar to the question we had in midterm 2017. Same force, okay, coming from the forearm muscle here, and the angle theta is provided with the vertical, okay, and the distances are provided relative to the elbow. So the elbow is the fulcrum in this case, right? And I have a load that is at a certain distance, A, relative to the force we're applying in the forearm. Now, question is asking you, use a torque. So here, determine the magnitude of the force F applied in the biceps muscle, okay, to balance, okay, to balance the system, okay. So if the system here is in equilibrium, this arm holding this load, okay, is in equilibrium. So I need to look at the net torque, and it should be equal to 0. Okay, so this will give me the force, the magnitude of the force applied in the bicep muscle. Now, we'll do it quickly because we've had a similar question, previous midterm. Net torque equals to 0. Now, if you remember, we had, so if I take you back, let's go back just to decide on the direction. Now, the only difference here is that the perpendicular component of force, as usual, only the perpendicular component is causing the torque. So F perpendicular will be equal to what? Because the angle now is with the vertical, not with the horizontal. So it will be F cosine theta. So F cosine theta, and it's causing a rotation that is, I'm sure you noticed, clockwise. Now, how about the load? The load is causing a rotation that is now counterclockwise. Okay, now the net equals to 0. That means I need to include only the torque coming from the load and the torque coming from the force. That's all we need to include. So if we do that, net torque equals to 0, round the fulcrum, round the elbow. Okay, now torque due to force, okay, plus torque due to gravitational pull. Okay, now I have first gravitational pull, that's the load. And then we have torque due to the bicep muscle force. So the load is at a distance A plus B. Okay, now this is the load. Again, so we have mass is 1.8 times gravity 9.8, and then minus force times cosine. Okay, remember it's the perpendicular component of force that is causing the torque in this case. So magnitude of force times cosine the angle 80 degrees times beta equals to 0. Now in this case, we're solving in a similar way. We're solving for the force F, and you put all the known values in one end and you divide by this factor F cosine, and you end up with B cosine. Okay, you end up with a value of force equals to 830. This will be our force. A second. Now, question 13, a person of mass 60 kilograms stands 0.4 meters from one end of a 2-meter long uniform plank of negligible mass that is being held in equilibrium by 2 vertical ropes attached to the end of the plank. Now, what is the tension in the rope nearer the person? Now, we had a very similar question in the lecture. Okay, so here, let's say the person is standing here, so this is the plank. Okay, so this is the plank, etc. And it's 2 meters. And we have a person standing at 0.4 meters. So let's say this is the person here at 0.5, okay, from the end. Okay. Now, what is the tension in the rope nearer this person? Now, of course, for me to find the tension nearer the person, like we did in the lecture, we choose the fulcrum being on the opposite end of this plank. Something we've done in the lecture. Why? We said because in this case I can eliminate tension 2, but I can still have access to tension 1. Okay. Now net torque around point A, so point A will be my fulcrum, equal to 0, rotational equilibrium. Now this will give me what? Tension 1 will tend to cause a counterclockwise rotation. So the torque here will cause a counterclockwise rotation. So CCW, the torque will be positive as a result. So torque due to tension 1 is positive. Now how about weight? Weight, sorry, this is not counterclockwise, mistake. So for tension 1, okay, for tension 1 it's actually clockwise, and it's not positive. Because it's clockwise, it's going to be negative. My mistake, so here, let's fix it. Torque is negative because it's clockwise. Now, for the standing man, right, so here it's going to be a counterclockwise. That's the counterclockwise. That's the CCW here. So torque Fg will be positive. Now we see it here. I do have a negative sign for the torque due to tension. So negative tension 1 times 2, okay, plus the mass, 60 times g gravity times 1.6. Of course, we're measuring the 1.6 from point A, okay, to where the man is standing. This will correspond to the 1.6. Remember, the man is 0.5 meters from this end here, 0.4, sorry, meters from this end. Now, solving for tension 1 will just give us the value we have here, 470 newtons. Now, question 14. A car drives over a weight scale, okay, weight scale. Now, when the two front wheels, okay, are on the scale, the weight measured is 6,200 newtons. Now, when the rear two wheels are on the scale, the weight measured is 7,500 newtons. How far, okay, how far from the front wheels is the car's center of mass if the wheels are 3.2 meters apart? Now, we're looking at this car, okay? And we're looking at the net torque, okay, in equilibrium around 2 points. So this is point F, the front, and then I have point B, the back. Now I'm going to look at the net torque around the front equal to 0 in equilibrium. All right, so this will give me what? So when the two front wheels, okay, were on the scales, it measured 6,200 newtons, okay? Now, in this case, when the rear, okay, so when the rear wheels were on the scale, the weight was 7,500. Now, so, and the other thing, sorry, here, yes. So if the wheels here are 3.2 meters apart, okay, so if the wheels are 3.2 meters apart, so I'm given the distance between point B, okay, point B and point F. So the distance is 3.2, okay? Now, in this case, I have the two normals, okay? So these are the two normals given by the scales. So the two normals will be these vectors pointing up. So 7,500 coming from the back, and then or the rear, and 6,200 coming from the front. Okay. Now we put the two together. Of course, one will be causing a counterclockwise, the other will be causing a clockwise rotation. So this one here will be from the back will be clockwise. So this is clockwise for the back. For the front, counterclockwise. So this is CCW. Now that's why for the 6,000, yes, 1 second. Yeah, one thing I forgot to mention is we also need the weight for the car, because if we're looking for how far is the front wheels, okay, how far the front wheels, so how far, sorry, from the front wheels is the car center of mass. if the wheels are 3.2 apart, we still need the total weight of the car. So for the total weight, I need to apply the net force acting on the car, okay, is equal to 0 because the force, or sorry, the car is not moving upward, so we're applying it along the y-axis, okay? So the two normals I have here, coming from the back and coming from the front, okay? Minus the weight, okay, because it's pointing down. So the two normals are pointing up and the weight is pointing down, so that's the minus, equal to 0. So that will give me a total weight of 13,700, okay? Now, here I have the total weight, and if I consider, like I said, the net torque equal to 0 around the front wheels, okay, I take the fulcrum or the pivot point being the front wheels. Now, if that's the case, okay, so I would say, so I'm not taking actually the two normals, sorry, it's actually the normal that is coming from the back wheels, right, causing a clockwise rotation. Okay, now the torque from the normal on the front wheels will be equal to 0, okay, because it's acting directly on the fulcrum. So you have torque coming from the back wheels, so that's negative torque, clockwise rotation, 7,500 times 3.2, plus, now for the weight, you see it's causing, the weight is pointing down, and it's centered around the center of mass, and it's causing counterclockwise rotation. So CCW for the weight, and the total weight we said is 13,700 multiplied by this value of x. So measured, x is now measured from the front to where the center of mass is. Now, solving then for x will give me a value of x equal to 1.752 meters. Okay. Now, question 15, we have the exact same question in midterm 2017. Now, where the angle alpha is with the vertical. Remember, when that's the case, the vertical component of force will be the cosine. F perpendicular is magnitude of force times cosine theta. This is the only difference in this case, okay? Now, the formula for torque is F perpendicular times distance r. So that will be F cosine, the angle relative to the vertical, times the distance r, okay? Now, of course, you need to check whether it's going to be a positive torque, if it's counterclockwise. Now, depending on where the fulcrum is, the pivot point is. Now, in this case here, the pivot point is on the left. The rotation will be counterclockwise. That will be a positive torque. But if we had a pivot point on the right, and we're applying a force on the left, okay, this will give me a rotation that is clockwise. That's if, of course, okay, but that's not the case in this problem. So the torque will be positive, and its magnitude, again, pay attention to the cosine when the angle is provided with the vertical, relative to the vertical. Question 16, which expression describes rotational equilibrium? Okay, so we've seen this again. So rotational means net torque equal to 0. Okay, so just rotational equilibrium. Now, question 17. You are walking a dog on a leash, pulling it with a force of 50 Newton. The leash is continuously acting on the dog's body at an angle of 115 degrees. Now, with respect to the direction of motion, which of the following is the value for the work of the tension in the leash after 17 meters? Now, these are questions related to chapter 7, okay, so related to energy. And work here of course, we defined it as being the scalar product, okay, between force and displacement, or it's equal to magnitude of force times magnitude of displacement multiplied by the cosine between the two vectors, okay, the cosine of the angle between the two vectors. Now here, okay, so in this case, the force I'm acting with is 50 newtons, okay. Then the so we're provided with the distance, the displacement is 17 meters, and also the angle, okay. So the leash is continuously, we're saying, acting on the dog's body at an angle of 115 degrees. So cosine 115 degrees. Now, in this case, you are applying a force like this. So maybe I can draw it in a different way. So let's say this is the force you're applying. Okay, this is the leash. Okay, so this is the leash. The dog is here. So let's say this cube here is the dog. And while you're applying that force, okay, so this is the angle it's making. So while you're applying this force, the object is moving, okay, this distance, 70 meters. Right. Now, what does that tell you? What does that tell you? So you're applying a force towards you, and the dog is still moving forward. Okay, that means you're expecting then to get a negative value of force. What does that mean? The work is done by the system, in this case, the dog. Okay, so he's doing the dragging. So he's dragging the motion. Okay, while you are pulling, okay, backward, but still the dog is causing the displacement because he's moving forward instead of following the direction of your force. Okay, so that's why we get this negative work. Okay, so question 18, concept question. If an object goes to the left, but one of the forces pushes it to the right, opposing its motion, which of the following is correct regarding the work due to this force? Of course, its negative work is done on the object. Okay, so negative work is done on the object, and we say the work is done by the object. Okay, the work is done by the object. It's similar to the question we had for the dog. Question 19, when an object does work, okay, on the environment, which of the following is correct about the speed and kinetic energy? Okay, when an object does work on the environment, which of the following is correct about speed and kinetic energy? Now we're adding work is done by the object, okay? Now here, the correct answer is the object becomes slower and kinetic energy decreases, okay? Kinetic energy decreases. So here, what happens, of course, is if the object is doing the work, okay, it's like I don't know, an object moving on a surface, okay, with friction, right? So of course the energy, okay, will be lost in the process, okay. So there's work being or energy that is being transferred to the environment, causing the object to become slower and the kinetic energy to decrease. And last question is, when positive work is done on an object, what best describes the way energy changes? Okay, when positive work is done on an object. Now here you have the work done on an object. Okay, like in pushing, so you're putting work into the system. So what happens is, in this case, kinetic energy increases. Okay, so kinetic energy increases. So here we're saying potential for the first one, potential energy decreases. Of course, if you're putting work into the system, energy overall should increase. So potential, there's no reason for it to decrease. Kinetic and potential energy both decrease. That's not correct. Option D, kinetic energy decreases, also not correct. And the energy does not change. That's not correct. Again, we're putting energy into the system, so you should expect energy to increase, at least kinetic energy in this case. Okay, great. That's all for this midterm 2016. Okay, so what's left are just questions related to chapter 7 from midterm 3s. Okay, previous years. We will cover these in the class. Okay, so I may post this later, or some at least of the questions from past midterms related to midterms 3. Otherwise, we'll cover them in class. Right. Thank you, guys.